Hi class, welcome back to part 2 of section 4.1 where we're talking about antiderivatives and integrals. This portion of the lesson is focused on solving what we call differential equations. So what is a differential equation? It's an equation that gives the derivative or includes the derivative of a function y in the equation. So some examples are just very straightforward. The derivative of y equals 3x squared using the y prime notation. Here again, derivative of y equals negative sine x. So using the dy dx notation. This one is the kind of function that sort of includes the derivative in the equation. So I could solve for y prime. I could isolate it. So it's sort of embedded in the equation. But because it includes a derivative, it's called a differential equation. Or here, where we use the f prime notation, derivative of f is equal to this function. So the derivative is given. It's an equation basically giving the derivative of a function y. So when we are solving differential equations, we have two types of solutions. One of them is called a general solution. A general solution is when you give your answer, so it's an equation. Okay, the solution is an equation that represents the family of all antiderivatives, the one that includes the plus c at the end, basically. So it's when you're looking at all possible functions that could have that derivative. For example, going back to the negative sine x one, so let's say here's our differential equation. dy dx equals negative sine x, and your job is to solve for y. You would take the antiderivative of negative sine, you would get cosine, and then you would add c. This would be considered the general solution because this is the answer for a family of functions because the constant c could vary. So it's not a specific function, but it's kind of showing you what all of the possible solutions could look like. And then here again, the derivative of f equals 1 over 2 rad x. So the antiderivative of that would be rad x plus c. So the solutions that add that constant of integration are called general because it's showing us all the possible answers or a family of functions that answers the question, or that could be an answer to the question or a solution to the differential equation. But sometimes we're given more information than just the differential equation. So sometimes we're given what's called an initial condition that allows you to solve for c. So you'd be given your differential equation plus 1 point on your original function, 1 point on the graph of your antiderivative. So what you could then do is use that point to solve for c. Oh, in this case c is 1. Oh, in this case c is 1. Or negative 1, sorry. And so you would have one specific equation that is not a family of functions, right? It's one specific function with one specific constant. That's what we call a particular solution. But you can't find that unless you're given an initial condition, which is a point on the antiderivative, a point belonging to the antiderivative. So how do we solve these functions? The first thing we do is we separate the variables. Now, in this chapter, chapter 4, this step is not going to be as important, but I'm going to stress it every time because later on in chapter 5, when we have both x and y in our derivatives, this will become very important. So we're just going to build the habit in now while we're doing some of these easier version of differential equations. So we prepare both sides for integration. You'll see what I mean by that in a moment. We integrate, which is when we find the antiderivative. We add our constant of integration to our general solution, and then if we're given one, we use our initial condition to solve for c. So remember, your final answer should be an equation for the original function, for the antiderivative, the function whose derivative is shown. Your solution should always end up being y equals blank. Okay? So let's try out a few. So in our first example here, notice we have our function in terms of t. So this is the derivative of y with respect to t. So when it's said to separate the variables, that's the first thing we do. That's where you take your variable of integration, if you will, or the thing you're taking the derivative with respect to, or the integral with respect to, and you bring it up to this side. So we would have dy is equal to 9t squared dt. That's the separate the variables step. Then we prepare both sides for integration. So we're going to take the integral of this side. So this is like the integral of 1 with respect to y. And then we're going to take the integral of this side. Integral of 9t squared dt. So that's preparing both sides for integration. Then we integrate. So what is the antiderivative of a constant with respect to y? Is just that constant times y. So this would just be 1y, which is perfect because I want my solution to be y equals something. So this is great. Over here, I can take the 9 out, right, and just multiply it to my antiderivative. This is going to be a simple power rule, so I'll do 9 times t cubed over 3, because you add 1 to the power and divide by it, plus my constant of integration. And then I simplify. So 9 divided by 3 is 3. So my solution, my general solution, that's all it's asking for here, would be 3t cubed plus c. So our final answer is solving for y, whose derivative was shown. Again, you can always check these answers. So the beauty of going backwards is that you have a way to check it. So I could take the derivative of y with respect to t, right? So then I'd have 3 times 3t squared plus c. So 9t, oh, sorry, plus 0. Whoopsies, derivative of a constant, 0. So then I'd have 9t squared. Check. That's what I had here. So this indeed must be the function, the general solution, where if I take the derivative of it, gives me 9t squared. Why don't you guys try this one here? So first, we want to separate the variables. We want to take the dx and move it to the right. So that was right here. So we have dy equals 2 over x dx. Then we prepare both sides for integration. So we want to take the integral of both sides. On this side, we're taking it with respect to y. On this side, we're taking it with respect to x. So the antiderivative of a constant with respect to y is just that constant 1 times y. So I just get y on the left. And then I have to remember that, maybe I'll split this side so I can take the 2 out. And I just have to remember that 1 over x is the derivative of ln of x. So the integral, or the antiderivative of 1 over x, is ln of x. And because I'm going backwards, and this x could be any number except 0, I have to put an absolute value around it to make sure the inside of my natural log stays positive when you're going backwards. So it's natural log of the absolute value of x plus my constant of integration. Lots of little details you got to remember, so always make little notes of those things so that you continue to remember them. Now, moving on to example 2, we're going to be looking at how to find a particular solution where we're given an initial condition. So it's giving me the derivative of y, which is the same thing as f prime, right? This is basically saying the derivative of f equals 10x minus 12x cubed. Find f of x. That's what this really wants us to do. When it says find the particular solution, that means find f of x, and it wants a specific function, no c, no constant c, because it wants you to solve for it. So what is f prime of x? F prime of x is the derivative of y with respect to x. So we should start by separating the variables, bringing the dx to this side. So I get derivative of y is equal to 10x minus 12x cubed times dx. So that's my separating the variables step. Then I prepare both sides for integration, the integral of that side and the integral of that side. This side I'm integrating with respect to y, this side I'm integrating with respect to x. So on the left, I just get y, right? 1 times y. On the right, I can split that integral up. So integral of 10x minus integral of 12x cubed. So that would be 10x squared over 2 minus 12x to the 4th over 4 plus my constant of integration. I do have to start with that. So let me simplify this a little bit. So I know that my function y, or my f of x, is equal to 5x squared minus 3x to the 4th plus some constant. Okay, so right now I don't know what that constant is, but earlier over here I was given a value for my function f at a given value of x, or a point on the graph, right? This is the point 3, 2. So I can plug in 3 for x and I can plug in 2 for y in order to solve for my constant c. So I have 2 equaling, if I do 5 times 3 squared minus 3 times 3 to the 4th, that's negative 198. So then my constant c, if I add the 198 to the other side, would equal 200. Okay, so what is my particular solution? My particular solution would be f of x is equal to 5x squared minus 3x to the 4th plus 200. That is my specific equation that has this point 3, 2, right? If I plug in 3 for x, I would get 2 for y. And if I take the derivative of it, would equal 10x minus 12x cubed. So why don't you guys try this one here? So again, for this one here, it gives us the f prime x notation, which, as we know, is the same thing as dy dx, right? They're synonyms. I write it this way just to get us in the habit of separating the variables. So I move the dx to the other side, and then I prepare both sides for integration, and then I integrate both sides. This side I'm integrating with respect to y, and this side integrating with respect to x. So the antiderivative of 1 dy is y. Antiderivative of 4 times e to the x is just 4 times e to the x. It's my favorite. I love it. And then I add a c. Don't forget to add your constant of integration. And then I solve for c, because in this one I was given an initial condition, a point on my antiderivative or on my solution that helps me solve for c. So I plugged in 0 for x here and then 3 for y. E to the 0 is 1, so this is just 4 times 1, and then if I subtract that from 3, I get negative 1. So my constant was negative 1. So that means my particular solution, the thing they were asking me to find, would be 4 times e to the x minus 1. What that means is this is the function where if I plug in 0, I get 3, right? Because that'd be 4 minus 1 equals 3. So f of 0 is 3 for this equation, and if I take the derivative of it, well, it would just be 4 times e to the x plus 0, or minus 0, so derivative of negative 1, 0. And so there we go. So it satisfies these two things. It has the derivative of 4 e to the x, and it has the condition where if I plug in 0 for x, I get 3 for y. So this is our solution there. Now for our last two examples, we're looking at situations where you have to go all the way from the second derivative to the original function. The particular solution is always referring to our original function f of x. But this time we are starting way back at the second derivative. So we need two initial conditions because I have to solve for f prime. I have to figure out what it is first in order to go all the way back to f. So on these examples here, I'm going to kind of, I'm not going to show the separating the variables step for these last two because I think it might just confuse things more. So instead what I'm going to do is use my f prime notation. So if I am taking the antiderivative of f double prime, so that's the antiderivative of 2 with respect to x, that would bring me back to f prime of x. So the antiderivative of the second derivative obviously would be the first derivative. This is the function who, if I take the derivative of it, gives me the second derivative. Over here, I'm taking the antiderivative of 2 with respect to x, so that would be 2x. And then, of course, I have to add my constant of integration. So I have a general solution here for my first derivative, but given this value here on the first derivative, 2, 5, so I can plug in 5 for f prime, and then I can plug in 2 for x, I'm able to solve for that constant in my first derivative. So I have 5 equals 4 plus c. That gives me c equals 1. So what I now know is that my first derivative is equal to 2x plus 1. So it kind of helps me go to that step we're used to starting at. Now at this juncture, I'm going to go ahead and rewrite this as dy over dx so I can illustrate the separating the variables step. So I'm going to take my dx and then bring it over to this side, separate my variables. And so I have dy is equal to 2x plus 1 dx. I will prepare both sides of my equation for integration. Integral of 1 with respect to y is y. Integral of 2x, that'd be 2x squared over 2. integral of 1 with respect to x is x. And then again, I have another constant of integration. So this y, or this is my f of x, right? Y equals f of x is x squared, 2's cancel out, plus x plus c. But that is why I was given another initial condition for just plain f, right? For my particular solution. So I know that when x is 2, f of x is 10. So I'll plug 10 in for my f of x, and then 2 in for my x, and solve for c. So I get 10 is equal to 4 plus 2, which is 6, plus c. So c is equal to 4 for my particular solution. So my final answer for example 3 is f of x equals x squared plus x plus 4. Now again, if you are not 100% sure, you can check this answer by just taking the derivative twice. Right, so I can check right now. I can say, well, let's say this is f of x, then f prime would be 2x plus 1 plus 0, right? Derivative of a constant 0. So that part checks out so far. And then the second derivative would just be 2. So that part's checking out because that's what this was saying. The second derivative was 2. I could plug in 2 for x, right? I could say, well, what is f of 2? That would be 2 squared plus 2 plus 4. 4 plus 2 is 6 plus 4 is 10. That checks out. I could check my f prime of 2, right? Because that was given earlier to be 5. So looking at my f prime equation, I do 2 times 2 plus 1. Yep, that's 5. Everything checks out. This is definitely my particular solution where f of 2 is 10, f prime of 2 is 5, and f double prime is 2. Now, lastly, in example 4, we are given a position, velocity, acceleration situation. We're being told that a ball is thrown upward with an initial velocity of 64 feet per second. So that means that that would be the value of my velocity when time is 0, right? My initial velocity was v of 0. So that's one initial condition, and then an initial height of 80. So that's like saying that my position function when t is 0 is 80. So that's what these initial velocity, initial height means the velocity initially, so when time is 0, and the height initially when time is 0. I'm using s here because it says find the position function giving the height s as a function of time t. So what I'm really looking for here, my final answer would have to be s of t equals something. I'm looking for an equation for the position function. So this gives us a little reminder that acceleration due to gravity is constant, right? It's negative 32 feet per second squared. So I start with that. So my a of t is negative 32. Now I can think of this as s double prime of t, right? The acceleration is the second derivative of position. So think of it that way. And I'll kind of do this the same way I did the first one. I'm going to kind of skip the separation of variables part for going from the second derivative to the first, because I think it'll be easier that way. So the antiderivative of the second derivative would be the first derivative. And this is with respect to t. So the antiderivative of negative 32 with respect to t would be that same constant times t plus my constant of integration. Well, the first derivative of position is basically velocity. So what I found here is a general equation for velocity. But I can solve for c because I was given this initial condition for velocity earlier. So I can plug in 64 for my velocity and then 0 for my time. And that just shows me that my constant is 64. So we have velocity function of negative 32t plus 64. Now remember, this is the first derivative of position. I keep using these terms interchangeably, but I want you to keep track. So acceleration is the second derivative of position. I just took the antiderivative to go backward one derivative, which is the first derivative of position, which is equal to velocity, right? So s prime of t and velocity, v of t, are synonyms, okay? And I had an initial velocity here. So I was able to solve for the constant in my velocity equation. Now I'm calling it s prime of t again, just to remember I have to go back one more antiderivative. This one, though, I'm going to call it ds over dt because I want to reinforce the habit of separating the variables, but I believe it's easier to do so with the first derivative. So the derivative of position, aka velocity, is equal to ds over dt, change in position over change in time. But I'm going to take that dt and move it to the other side, separate my variables. I'm going to prepare both sides for integration. The antiderivative of 1 with respect to s would just be s. So there's my position function. This is negative 32t, so I'm going to use the constant multiple rule, which says just multiply your constant to the antiderivative of t to the first, which would be t squared over 2. The antiderivative of a constant with respect to t would be that constant, so 64 times t, and then I have to add my constant of integration. So I was also given earlier an initial height, right? So my position at time 0 is 80, so I can plug in 80 for my position and then 0 for my t, although maybe I'll simplify this a little bit. Let me simplify first before I plug anything in. So my position function is equal to negative 16t squared plus 64t plus c. I'll plug in my initial height for position and then 0 for t. And that tells me that my constant is 80. So these constants are also thought of as the initial values of both velocity and position. So you can basically skip these steps because these functions were polynomials. So the constant is going to equal that initial value because all the expressions that have t, when you plug in 0 for them, go away. So my final answer for this one, my position function, would be s of t equals negative 16t squared plus 64t plus 80. Okay, so now I can answer questions. Now that I know my position equation, I can answer questions like this one. Determine when the ball hit the ground. Well, hits the ground, that would be when position equals 0. Now that I have an equation for position, I can just plug in 0 for it and figure out, okay, what time, right, solve for t, what time was it when the ball hit the ground? Now, I'm going to try factoring this one because it looks like I can divide each of these by 16. So I'm going to try just factoring out a negative 16. So that'll change this to negative 4. And then this one to negative 5. And then I can factor from there because I know if I did t minus 5 and t plus 1, the negative 5 times 1 would multiply to negative 5, and then negative 5 plus 1 would add to negative 4. So I know that it could factor into these two factors. And since it's all equal to 0, I can set each of my factors equal to 0 and solve. So I know at one instant would be at 5 seconds, and then the other one would be at negative 1 seconds, which doesn't really make a whole lot of sense. So we're going to look at this 5-second answer. So from this information, so I was told that a ball is thrown upward with an initial velocity of 64 feet per second. It was starting at an initial height of 80 feet. So it must have been thrown off of some sort of, I don't know, bridge or something like that. We were able to get an equation for position by doing this anti-differentiation process using these initial conditions. We were able to find an equation that represents the position of this ball being thrown upward, and then answer questions like this one. I could answer any question really about this ball. I could find its maximum height, I could find out what time it hit certain heights, and I can find out how long it took to hit the ground. So it looks like it was thrown up with an initial velocity of 64, and then 5 seconds later it would hit the ground. So that concludes this video, and I look forward to seeing you in the next. Bye.